Okay, welcome everyone. Today is March 16th, and this is another of our batch working group bi-weekly calls. My name is Mati, and I'll be your host today. On the agenda, we have Jacob Tomlinson to talk about Dask and Kubernetes. So take it away from here, Jacob.
Right,
And
awesome.
sharing,
Yeah.
and you should be able to share your screen.
Perfect. Right, okay. You should be able to see
Yes,
my slides. Please shout if you can. Yeah, so hi, my name's Jacob. I'm a Dask developer, and I also work at NVIDIA on some like data science tooling stuff. I wanted to come along and kind of talk about Dask. I was chatting to Kevin, who came along to a talk that I gave at PyData DC just about Dask and Kubernetes and how we run Rapids on Kubernetes, which is the data science tools that we work on at NVIDIA. And he kind of suggested that the kind of how we have implemented like our operator in Dask might be interesting to this group. We have some kind of batch resources. And so what I'm going to kind of aim to do is give a bit of an overview of Dask, just to give you an idea of what it is, and then talk through a bit of the history about how we've like deployed Dask in various different ways, and then talk about the like recent work that we've done on our operator and the resources that we have there. So yeah, you can probably tell by my accent, I'm based in the southwest of England. Apologies for the time zone mix up in me joining. My main focus areas are on kind of deployment of scientific and data science workloads in the cloud and on HPC in various places. So I'm not by any means a data scientist, but I like help data scientists get their work running at scale. So here's like a collection of logos just to give you like a gist of my skill set and what I'm interested in. So let's dig into like Dask and what Dask is. Some folks may have heard of it, some folks may not. It's a popular tool in the Python ecosystem. And Dask is a software library basically to help Python developers parallelize their work. We have a bunch of code in there to help you if you already use libraries like NumPy, Pandas, scikit-learn, whatever, but you can also build completely bespoke and custom kind of distributed Python applications with Dask. So Dask's been around for a while now. I think it was like first created in like 2015, 2016. And it's kind of a core component within like the PyData ecosystem. And like here's a quick look at like how you can write some low-level Dask code. Right, so you can write regular Python functions and you can decorate them with Dask delayed, or you can also, we have like a futures API as well. But what this effectively does is it makes these functions, it defers the execution of these functions. So as you kind of call them and they call each other, Dask like builds up a task graph under the hood, but it doesn't actually execute any of the code until you kind of tell it to. You can say like .compute on any kind of deferred object, and it will execute that. So you can just see here's like a little kind of visualization of a graph that you can build up with some minimal Python code. This is great if you want to really like get under the hood and play around with designing kind of lazily evaluated Python code. But Dask also has these like high level collections that have like re-implemented popular APIs using this, like Dask delayed and Dask futures, so that it can be executed on various different schedulers. So if you use NumPy, then you can come use Dask array. If you use Pandas before, you can use Dask data frame. These collections kind of implement those same APIs, but they kind of chunk everything up and distribute them. So say you want to work on like a really large array of data, an array that's like larger than the memory that you have on your machine. Typically you would do that in NumPy, but you would run into like out of memory errors. So Dask's Dask array library follows NumPy's API. You can do all kind of normal NumPy stuff, but under the hood, Dask will like chunk that NumPy array up into lots of smaller NumPy arrays, and it will swap them in and out of memory and do kind of out of core computation so that you don't run out of memory. And it has like a re-implementation of a load of algorithms to kind of accommodate that. So say you wanted to, I don't know, do like a mean of your array or something. Dask would go through and take a mean of each chunk, cache all the results, and then when it's finished, it'll bring all those together and do a reduction and calculate the final mean. And so this is great if you want to work with large memory data sets, but it's also great if you want to leverage more than one machine, because you've got this graph. It can be evaluated by a scheduler. It doesn't have to be evaluated by the machine that you're on. I mean, machines these days have got like bonkers numbers of CPU cores anyway, and Python isn't particularly well known for leveraging lots of CPU cores. So Dask is like super useful just on like a modern laptop for getting the best out of the CPU that's in there. But also you can go and grab a load of machines from your preferred cloud provider or whatever and run a bunch of Dask workers that are all talking to a Dask scheduler, and then your machine will be submitting the work through the Dask client and kind of distributing across. So those are the kind of two big benefits that our users see, as opposed to using the like regular APIs. And one of the other nice things is that scheduler has like a bunch of like extra things that are nice. And one of those that people really like is the dashboard. So it kind of shows you the graph, it shows you progress bars of how it's working through the workload. It's got like flame graphs in the profiling section, so you can see where your code is fast and slow. There's like lots of extra things you can do by having this graph and executing it on a scheduler. But you can see here is like a quick example of taking like a big random array, specifying its chunk size. This is like this is like a 75 gig array, but it's chunked into like 1 gig chunks, and that will be distributed across a few machines, and calling mean on that will spread that work out. So that's pretty neat. The dashboard also integrates into Jupyter Lab. So a lot of our users use Jupyter as their kind of development environment for doing their data science or traditional science workloads. And so having the Dask dashboard straight in there, being able to just look at what's going on when you're running these jobs is really, really helpful. One of the other nice things we can do is, because the scheduler starts working through this task graph and it starts executing each individual task, it can build up kind of a forecast of how long the overall graph is going to take. Once it's run a few tasks of like each category, it should have some time estimates, and it can kind of extrapolate that out and say, oh, what's the most efficient way I could run this? If I had another 1,000 CPU cores, would I be able to run this faster? And if yes, it can request more workers. If Dask has been deployed in a way where there's like a handle it can pull to get more resource, the scheduler can pull that handle and scale up. So you can see like a screenshot of the dashboard here, where the bottom plot is tasks being run on cores, and you can see over time as it's running through, like the number of rows in that graph is increasing as more capacity is coming online, as it's asking. I think this was a Kubernetes workload, so it's like asking, it's just scheduling a load of pods, and this is kind of as they're coming in, that you can see like waves of new pods coming in as the cluster autoscaler is like pulling new nodes in, and everything's kind of speeding up and getting faster and faster. So that was like a super high level, like Dask in 10 minutes. But just to like quickly recap, like Dask is this Python library to help folks in the PyData ecosystem scale out their work, right? If you use NumPy, Pandas, scikit-learn, whatever, Dask can help you kind of move beyond the constraints of the memory of your machine, and it can help you distribute onto a larger cluster. I also want to just quickly like mention like the broader project that I work in. It might help just to give you a bit of context. So I work for NVIDIA. I work within a project called Rapids, and Rapids is like doing a similar thing to Dask in that it's kind of coming into the PyData ecosystem and providing acceleration to folks using libraries like NumPy and Pandas and things. But this is being done by like re-implementing NumPy or re-implementing Pandas, but using CUDA underneath and leveraging GPU parallelism. But one of the really neat things, because Rapids is kind of copying the APIs of Pandas and NumPy and whatever, and Dask wraps those APIs to distribute them, you can add Rapids and Dask together, so you can have like GPU level parallelism to get like hardware acceleration, but then you can also scale that out over many nodes with many GPUs in to get like distributed parallelism as well. So we see some like nice speed ups combining Rapids and Dask together. So if you have a node with a bunch of GPUs in, it'll run a lot faster than like many nodes with many CPU cores. So this is kind of, we have a lot of customers coming to us, I guess, saying like, how do we deploy Rapids? How can we get like these GPU libraries? How can we get our PyData work to scale out. And so we kind of, this is a pretty common stack that we end up with, right? The customer comes to us, they say, we use cloud provider, whoever, and we use Kubernetes to abstract away that provider. And then like, what do we do next? So we often come along and say, right, you install Dask using the Dask operator, and then you run your Rapids workload on top of that. So we've been putting like quite a lot of development effort into Dask and contributing upstream there to make sure that that's like a seamless and pleasant experience on Kubernetes. So now that we've like talked a bit about what Dask is, let's have a look a bit about how we run Dask and how it's actually deployed and how we've like changed that over time. So like bare minimum, I want a distributed Dask cluster. You have to start a Dask scheduler somewhere. You can just, if you pip install Dask, you can run Dask scheduler on the command line. That will start the scheduler process. And then you run Dask worker, tell it where the scheduler is by its TCP address. The worker will connect to the scheduler. You can run many workers on many machines, as long as they can all, as long as the network allows for them to talk to each other. You can have lots of different machines connected into that scheduler. And we do support other protocols as well as TCP. So if you've got exciting hardware like InfiniBand or something, Dask can leverage all that too. So you can set all this up locally if you want to. Just run Dask scheduler, run Dask worker, and then in Python, you import like a client from Dask distributed. You connect that to the scheduler as well. And then any of your code that you run that uses Dask will kind of start handing that off to the scheduler for execution on the workers. This is kind of, you basically would never do this, but I just kind of wanted to show these are the pieces, right? These are the moving pieces that we're trying to think about. How do we make it easier for people to run this? So kind of the bare minimum is like, oh, I've got a decent laptop, I've got a decent workstation. How do I like leverage the whole machine? We have this nice convenience class called local cluster, which you can just import and instantiate in Python. And that will create those subprocesses for you, right? It creates the scheduler, creates the workers. It uses some kind of heuristic to decide what kind of ratio to use, because if you create new processes, there's like a little bit of overhead to that. But if you have too many threads within your Dask worker, like GIL-bound code will kind of suffer from that within Python. So if you use pandas, like sometimes that behaves well, sometimes it doesn't behave well in terms of leveraging many cores. So it tries to like balance like, oh, you've got 12 cores, so I'm going to give you 4 workers, and each of those workers are going to have 3 threads, and that will be like a good balance maybe for like the average workload. But you can tweak and tune this however you like, really. But this is kind of a common pattern that you see throughout Dask's development is you have a class that you import, you instantiate it, and that class spawns subprocesses through some mechanism. So in local cluster, that's literally subprocesses on your machine. But if we have a look at like the HPC libraries we have a package called Dask job queue, and that's got cluster managers for kind of all of the common resource managers within the HPC ecosystem, right? PBS, Slurm, SG, whatever. And they work in exactly the same way. So the example from the README here uses PBS cluster. You can see this just importing PBS cluster and instantiating it. And this is kind of intended to be used from the head node of an HPC. Maybe you've SSH'd into the head node, or maybe you've got a Jupyter service or something that gives you notebooks on the head node. And then you import one of these classes, you instantiate it, and the scheduler gets created as a subprocess of your notebook or your Python session on the head node. But then all of the workers get submitted as jobs into the HPC. This is pretty nice if you have like a nice fast allocation response time, especially if maybe you've got like an HPC that's got lots of large jobs going on. Each worker is like a small job, and often they like fit into lots of gaps within the scheduler. So an analogy that one of the other maintainers uses, it's like pouring sand into a bucket of rocks, right? If you've got a big HPC, you can kind of pour Dask workers in, and they fit into all the nice nooks and crannies within the system. It's a good way, especially on interactive queues, to leverage some resource. But again, this is kind of based around that model of you have a node somewhere that you're interacting with, or you're running like a batch workload on, and that is creating a subprocess and spawning more resources being allocated. So when we came to implement kind of the early Kubernetes functionality in Dask, this followed that same model. It assumes that you're on a pod inside the Kubernetes cluster already. I used to work in weather and climate for the UK government, And we had a Kubernetes cluster. It had Jupyter Hub on. It would spawn us like a notebook, and we would be in there. And then from there, we wanted to burst out into like a DAS cluster and scale out within Kubernetes. So it would work. The classic implementation of this would work in that same way. Right? The scheduler would create it as a sub process of your Python session in your pod, but then it would, using like a service account and some credentials, it would create more pods that would have the workers in and kind of expand within the Kubernetes cluster. Again, this assumes that all the network connectivity is there. This did evolve over time. We kind of updated this a bit so that the scheduler would get created as a pod rather than a sub process. We added some functionality to the cluster manager where if you weren't inside Kubernetes, it would port forward automatically or look for a service and check whether it could hit that IP and kind of, go through a load balancer or something. But this always kind of felt as like that extension of creating sub processes in an HPC-like system. And it didn't necessarily feel like particularly Kubernetes native. We also, within the Kubernetes space, we have a Helm chart, which is kind of more of like a community maintained thing. But this chart has just got like a deployment with a scheduler in, a deployment with some workers in that connects to like the scheduler's service, and a deployment with a Jupyter notebook in. So it's like a nice little self-contained app that you can deploy onto a cluster, and it gives you Jupyter plus a DAS cluster, and it can do some of the things that you want to do, and it's quite a nice way to get started. But it's got no mechanism for asking for more pods. It can't scale up and down automatically. You can scale up manually if you tweak the deployment. But there are some challenges around that because the Dask workers are like fungible until you give it some work to do. As soon as the scheduler starts dishing work out, the workers kind of become stateful for a while. They've got things they're keeping in memory and they're communicating with each other and stuff's going on. And if one gets lost, all the others have to like recalculate all of the memory that it had, and it can recover from errors, but you can't just kind of add and remove workers randomly. You kind of want the scheduler to be involved in that decision. And so like having a deployment in charge of like scaling down, you need to make sure the cluster's like idle before you scale down. And there's a few kind of challenges, but it's a nice little way of getting going with Dask. And the last thing kind of historically about how we deploy Dask as well is we have another project called Dask Gateway, which is intended to be like a cluster provisioning service, right? It's a thing you can install. It has its own API and you can say to it, can I have a Dask cluster, please? And it has a few different backends that it can spawn Dask clusters on, Kubernetes being one, but it can also use Yarn to spawn on like a Hadoop cluster. It has some HPC backends, although not as many, I think, as Dask Job Queue. But the gateway will kind of have the credentials. It will interact with the resource managers. It will kind of create things. And then it proxies everything through one like traffic proxy. So you have like one ingress point where everybody's like connection to their Dask cluster is like multiplexed through that traffic proxy. And so like this is really good if you want to kind of insulate your users from the back end. If you don't want them to even know they're on a Kubernetes cluster, they just know that they have compute and they can ask for like cores and memory and whatever. It's like that next abstraction down. It's kind of nice as well if you have many of these compute platforms and you want like a consistent way to come in and ask for a Dask cluster. But as I say, this is like abstracting your users away from Kubernetes. It's not like a Kubernetes native solution. So coming around to like the work that we've been doing for like the last year or so, we've been working on kind of what we're referring to as our like Kubernetes native support. This is like creating Dask clusters in a way that like feels natural on Kubernetes, leverages the tools and features that it has, but also like exposes your users to that environment. So it's very much like Kubeflow or something like that, right? Where your users have credentials, they're creating resources, they're interacting with the Kubernetes API. The Dask operator is there for that community, really. So our controller is built with Kopf. It seems like a nice way to write controllers. Given that we're like a Python community and we have a lot of Python developers, it made sense to write our controller in Python, just to maximize the number of maintainers that would be around working on things. I nearly went down the Go road, but then I realized it'd be like me and one other person maintaining this within the Dask community. So we went with Kopf, and things seem to be going well with that so far. So the way we implemented this is we created a few custom resources for Dask. We have like a top level Dask cluster resource, which kind of represents a whole cluster. Within that, there is like a Dask worker group resource. So you can have like many different worker groups. And so you can kind of configure your workers differently and say, right, I want a group of workers that have got, you know, a CPU to memory ratio like this. I want another group of workers that have got maybe like a high memory to CPU ratio. Maybe I want a group of workers that have got GPUs. And Dask has got like some resource tagging that you can use to do almost like node selector stuff. You can say like this task should run on workers like this, and this task should run on workers like that. And they can all like auto scale independently as well. So it's kind of neat if you have like a long Dask graph where there's like a chunk in the middle that like blows out memory, or there's a chunk in the middle that really benefits from GPU acceleration. You can have different groups of workers to accommodate that. And so these are kind of, they have the like service spec and pod spec kind of nested within them, kind of inspired by the job resources that existed. So you can kind of come in and say, this is what the scheduler should look like, this is what workers should look like, this is what the server should look like, this is how I want my scheduler to be exposed, and the dashboard and things. We then also have some like complementary resources. We have the Dask autoscaler, which is pretty much like an HPA, except that it communicates with the scheduler and it asks like, do you want to scale up? Do you want to scale down? When scaling down, which workers do you want to remove? Or it can say like, I want to scale down from this number to this number. Can you drain the memory of certain workers? And the scheduler will drain like the workers with the least amount of memory usage and that kind of thing, so that they're safe to remove. And there's interaction between the controller and the scheduler to decide and to kind of work around the challenges of the like semi-statefulness of Dask. And then the last one, the third one on this list here, which I'm going to talk about a little bit more, is the Dask job resource. Which is probably going to be of interest to this group. So the Dask job is kind of inspired by the PyTorch job in Kubeflow. It's kind of like a batch thing that you can submit, and it will run kind of end to end through like a pod. And if the pod exits cleanly, the job is kind of complete and successful. But the way it works is you have like a pod spec for your job, your workflow. So if you've got your Python script that does your Dask code, you put that in a container, you have your pod that runs that container. But then it also has like a Dask cluster resource that runs alongside it, and it pre-configures that pod, the workflow pod, with all of the Dask connection stuff. So the user code doesn't need to know where the Dask cluster came from. They just create a client. They don't need to configure it in any way. It will just connect, and then it will leverage the cluster that's adjacent to it. And then once that pod is completed and the workflow is finished and it's successful, the Dask cluster will be removed so that it won't be using any resource on Kubernetes anymore. So this is quite nice if you want to come in and submit like one-shot training jobs or something that leverage like a Dask cluster that you're not going to be necessarily monitoring or interacting with. And you can do all this via kubectl. And the last thing is we also made sure that we were fulfilling that Python API that our users are kind of accustomed to and expect. So we have like a new implementation of kubectl, which all it is doing under the hood is creating the custom resources, and then it's still got some of the nice stuff around it. Like if you're outside of the cluster and it can't access, if your service doesn't use a load balancer or no port or anything, it will like open a port forward automatically, unless you tell it not to. And there's a few like quality of life things for users, but from there, and they can just import the class, instantiate it. And then if you go on, kubectl, you can list the Dask clusters and see the cluster that got created. So we've got to this point now where we've decoupled our Dask cluster from the actual resource, and it feels a lot more kind of like it should do, I guess, within Kubernetes. So just going to kind of round off this with one kind of comment on how this has been going. So we've had the operator available for maybe 6 months or so, and Flight, which is like a workflow management tool, has kind of picked this up already and run with it. So it's kind of nice to see this, because Flight uses Python, right? And it kind of decorates functions in the same way, if you want, as Dask, for designing your kind of end-to-end workflow of your data processing or ML or whatever. But it's working at like a higher level, right? You kind of have your pipeline of, I want to load some data, I want to transform it, I want to train a model, I want to do whatever. You define all of that in Python with Flight. And they now have a Dask plugin, so that each of those steps within their kind of overall workflow can spawn a Dask job resource and run within a Dask job resource. So you get like an adjacent Dask cluster And you can kind of configure that. You can see there's a blog post on the Dask blog kind of going into more detail about this. But this is kind of nice to see folks that are building things kind of with the Kubernetes APIs and implementing their workflow manager, because we've been able to build the Dask operator with CRDs and kind of make it feel a bit more native. They can just come in and pick up our resources and integrate them into their workflows. And so yeah, that was like a nice success. So that was kind of all I wanted to go over. I left some time at the end in case folks kind of want to ask questions or chat about anything or dig into anything particular. But hopefully this was just an interesting overview of Dask and how we run on Kubernetes.
Thanks a lot, Jacob. There is one question in the chat. Will Dask terminate pods when workload is finished? I guess that goes back to one of the initial slides where you were presenting how autoscaling was working and how it was expanding the pool of workers.
Yeah, exactly. So yeah, when it's auto scaling like that, it will expand as long as the scheduler thinks that expanding will get you through the graph faster. And then as you get towards the end of the graph, it will start to contract again and scale away. You can scale all the way down to 0 workers if you want to. But like the Dask cluster resource is like an always on thing, right? Which is why we added the Dask job, so that you've got like this pod that runs to completion and then kills the Dask cluster at the end. So there's a few different ways that you can get it to like scale up and down and handle that life cycle.
Okay, cool. Aldo, go ahead.
Yeah, first to confirm if I understood correctly, the Dask cluster lifecycle is completely independent from the job, right? So a cluster outlives one or more jobs. Is that correct?
Not necessarily. I mean, you can do it that way. If you create a Dask cluster resource and you use kind of regular like Kubernetes job resources, that cluster can like exist independently. The jobs can reuse that cluster. But then like the Dask job resource itself, the intention is like when you create that resource, the controller will create a Dask cluster and the pod. It will run the pod all the way through, and as soon as the pod like completes successfully, it will then clean up the Dask cluster again.
Oh, okay. So that's one possible mode. So that actually sounds very similar to Ray job. So
sure, yeah.
So now in that mode of operation, then each cluster is a single user basically, right? There is no multi-tenancy.
Yes. Yeah, it's typically like Dask overall is just assumed that it's a single tenancy. Usually you just think of a Dask cluster as doing like one thing at a time. There's no kind of prioritization of work or whatever. It's just whoever submits a graph first gets the graph, which is kind of why we treat them as pretty like ephemeral things, right? You create a Dask cluster with a scheduler and workers, you run a thing and then you tear it down again. They're pretty lightweight and cheap to throw up and down. We see a lot of folks using like Kubernetes to handle the multi-tenancy part, and then users kind of creating lots and lots of ephemeral Dask clusters within that that are their own.
Great. One last question, if there are no others.
Yeah, go ahead. I think Abdullah was next, but
yeah, Abdullah can go ahead.
Yeah, I was trying to change the name. I don't know why I keep getting logged in with work group. Actually, actually, I had similar questions to Aldo's, and I guess like, can you summarize what's the difference between Dask and Ray? Like, I mean, on the surface, it seems to me that they are similar. Maybe not. I don't know.
They are similar. Dask has kind of been around a little bit longer, I think. You can do like, is it Dask on Ray? They like work together. So instead of using like Dask's scheduler, you can run Dask on top of Ray.
Okay.
But yeah, it's kind of separate communities within the like distributed Python space.
But the difference between them is basically Ray focuses on the orchestration and part of.
Yeah, you get some similarities because there's Modin as well, right? Which uses Ray or Dask to like do kind of similar things to what we're doing with the Dask collections, to like accelerate your like pandas work and things. So yeah, it's kind of a similar tool to Ray and Modin kind of together, if that makes sense.
And would you say that, like, because Ray got its fame mostly for training workload, at least that's my understanding, is Dask in the same?
Not so much, yeah, because there's Ray Tune, right, which is like quite popular. Dask is like, so I come from like a weather and climate background. I used to spend a lot of time working with like large multi-dimensional array data sets of like weather forecast or whatever, numerical weather forecast. And so we used to use Dask array a lot for working with that kind of thing. There's like a big community called Pangeo, which is like a group of geoscientists and folks within that kind of space. They have a stack of tools. Dask is one of them. They've got like a higher level tool as well called Xarray, which is like it's a bit like pandas for multidimensional data. It's like labeled axis tooling. So the Pangeo folks are always interested in running Dask on Kubernetes. And then we see a lot of folks in like the financial services sector. So we see a lot of like ETL type work done with Dask. Same with like Rapids, but these things can all be kind of used together anyway.
All right, thanks.
Hey Jake, it's Kevin. Thanks for actually listen or coming to this talk. It was very good. Or I'm not coming to it, but I'm glad that you decided to do it. One question I was wondering, I'm always interested in how all these different schedulers kind of work together. How much effort is it for like the Dask scheduler to work with like Slurm, HPC, Yarn, and Kubernetes? Like, do you kind of take a like, I guess, how do you have like a scheduler for Dask that also works with these different schedulers without them conflicting?
Well, I guess it's like different levels of like, you think about like the Slurm scheduler or something is like scheduling processes generally, right? Whereas the Dask scheduler is scheduling function calls within like a collection of processes. So they kind of work hand in hand in that like Dask just says to these other schedulers, like, can I have some workers, worker processes, please? And then once those have been created, the Dask scheduler can kind of feed them functions to execute as it needs to. So yeah, does that answer that?
Yeah, I guess, because like what I've always wondered for, it's always kind of, I found tricky for me is like the hardware requirements for a lot of these things were really different between like Slurm and Kubernetes. And like, I wonder if you have like kind of like a generic interface for scheduling for like of a GPU workload with Dask on Slurm and kind of have to sort of change, like you handle a lot of like what the S runs and the S batch stuff in Slurm and the Slurm one, right? Like you're kind of calling out to the scheduler, and then I guess from like a user standpoint, I don't really understand how that like interacts with like the queuing system and the like those types of things, which is always what I find it gets very hairy very quickly.
Yeah, no, I know what you mean. So I guess like in Dask job queue, this like in the Slurm implementation, it's just using like SBatch, I think, to submit the workers. Like each one is a separate allocation, and you are then just kind of beholden to the queuing system as to when it's going to give you these workers. And so like where's that graph of it auto scaling? Slide transitions on those. I think this slide. Yeah. So in something like this, you can see the graph at the bottom where like new workers are coming online and they're starting to pick up work. Like this would look the same with one of those where maybe Dask job queue has used SBatch to like start a load of workers, but then you're going to sit in that queue. The Dask cluster might just be like idle until some workers appear. And you might not get them all at once, right? You might get like fed to you. And so you'll see this kind of ramp up over time. You may also kind of lose resource and see it ramp down again if you hit the wall time or whatever on an HPC. But it's, yeah, Dask is working on the like millisecond level of scheduling maybe, whereas I feel like Slurm and things are maybe working more at the minutes to hours to days kind of level of scheduling.
All right, well, no, thank you. It's very well explained.
Roland, you're up next.
So thanks for that clarification about scheduling. I had the same question. But going a little bit back to the architecture, so do I understand correctly that there are actually 3 kinds of pods for a job, like the workers,
Yeah.
the scheduler, the task scheduler, and the workload itself, the driver, let's say?
Yeah, we typically call that the client, but yeah, there's like three types of things. So in like a batch situation, you would have those kind of 3 environments. In like an interactive setting, that driver pod would probably be like a Jupyter pod that's been spawned by Jupyter Hub or Kubeflow or something.
Okay, sounds good. Yeah, good to know.
Thomas, you had a question?
Hi, yeah. Jacob, I had a question about I just want to check one of the things that I think I picked up about Dask Gateway, and maybe, well, I guess like it is maybe kind of related to that question of like the hairiness of dealing with job schedulers. And was that, would you say that it's correct that from the user perspective, from the notebook perspective, one could create a notebook where the abstraction, you know, the abstraction layer allows them to like talk to a batch scheduler kind of backend at one location, and they might be able to move their notebook to another context where the backend scheduler is actually the Kubernetes, Dask Kubernetes, and they would they need to make changes to the notebook in that case, if both contexts were running Dask Gateway? Does it help with that, or are there still changes that need to be made? Sorry.
No, it does help with that. So Dask Gateway it has like a bit of, grab the docs a sec. Oh, can't type. So if I go to like the usage, so when you import Dask Gateway, you have to like connect it to the gateway. But this can be like pre-configured via an environment variable. So you can just create this without any arguments if it has been set. And then when you want to create a cluster, you can just call like new cluster. So if you as like an HPC admin have like pre-configured the user's environment to know where the gateway is, then the user code can just kind of instantiate a gateway, call new cluster, and something will get made for them. And then if you move them to like another session with a different config, you know, environment variable, their code will still work with a different backend. That totally is a thing that we see happen.
Okay.
Another thing we're trying to do is we have another project called Dask Control. Right, there's lots of sub projects in Dask. I can't type it all today. Dask CTL.Dask. Sorry, Zoom controls are in the way of where I'm typing and I can't see what I'm doing. Oh, maybe this. Maybe I put it somewhere else. There it is. So we have another project called Dask Control where you can kind of use any of the cluster managers that we have: Job Queue, Dask Kubernetes, Dask Yarn, Dask Cloud Provider. Like there's a lot of different backends. And so you can kind of specify like creating a cluster should use this class with these keyword arguments, and then in the user code they can just call like create cluster and either provide like a path to a config file, or you can kind of pre-configure this again in the user environment. And this is meant to satisfy the same thing, right? Of like, if you're in a situation where you're like an admin of a cluster and you want to give users like templates and kind of predefined Dask clusters, and you don't want them to know too much about the ins and outs of where the work is running, you can kind of pre-configure this stuff for them. So Dask would just launch in the right place.
Okay, I didn't know about that one. Thanks.
Sure.
There's a question in the chat. Curious to know what happens with the Dask cluster if the client pod dies.
Sure. So one of the things we haven't decided yet is kind of whether we want to. So the normal like job you can configure to be like, you know, you should run this number of times, or you should retry this number of times, or you should go parallel this number of times, right? There's like a few different modes of like the Kubernetes batch job. So the moment we've just implemented the like, you should run start to finish, and if you succeed, you delete the Dask cluster. I think at the moment, if it fails, the Dask cluster remains and it will restart the pod and allow it to like retry. we've been having discussions about like, should we add like a maximum number of retries, and if it reaches that, maybe the DAS cluster gets removed, or maybe like, yeah, that's probably the route we want to go down, but we haven't implemented that at the moment.
Go ahead, Aldo.
Yeah, we are at time, but one question we usually have is which gaps have you found in Kubernetes for supporting Dask, and if you have any high-level petitions.
Yeah, no, it's a good question. I think I have to think about that maybe and get back to you, because it's been pretty good, like trying to, with the batch job stuff that we've been doing, we've been trying to figure out how to like reuse what exists already in the batch API, and none of it felt like it quite fit with what we were trying to do, which is why we ended up just going, our controller just creates a pod. We do wonder whether we should like create a job, or maybe some kind of different kind of job. But I guess like one of the reasons we've done all of this is because we have these like deployment doesn't work for what we want to do, and stateful set doesn't work for what we want to do in terms of like groups of workers. And so maybe the gap that we've tried to fill with our custom resource is this kind of like semi-stateful type of pod, where we kind of need to be able to flag that this pod is stateful for like a period of time, and then unflag it. That might be the only thing that jumps to mind, really.
Oh, I see. So each kind of pod, the workers are individual pods, the scheduler is an individual pod, and so on, and the client, of course.
Yeah.
Yeah, if you can think of ways that the existing APIs can be improved, so you can reuse those implementations rather than managing pods, bare pods. For sure, let us know, file issues, or just just ask questions in the Slack. In particular, in this group, we have been adding a lot of new features for job, for example, index job, or job failure policies, which I think you've been dealing with. So yeah, if you can migrate to job, or if there are some things we can add to make it so that you can migrate, that could help simplify your architecture.
Yeah, that would be great.
Okay, with that accent, we can close today's call. Thank you very much all for the day, and see you next time in 2 weeks. Bye all.
Thank you.
Great. Thanks for having me.